Welcome back to Understanding Python. My name is Jake, and today we'll continue our mini-series on concurrency by covering multiprocessing. Unlike threading, multiprocessing is a bit more complicated, but it's also the best option for computationally intensive tasks. If you haven't seen my video on threading, I recommend you watch that first, as it will help you understand the differences between the two. If you have, then let's get started. Multiprocessing, unlike threading, is a great way to speed up CPU-bound tasks. But what do we mean by CPU-bound tasks? These are tasks that take a lot of processing power, specifically from the CPU, to complete. They're typically things that perform complex calculations, manipulate a lot of data, or just run generally computationally intense algorithms. Something like image or video processing would also count. Now, in order to use multiprocessing, we're of course going to have to import the multiprocessing module, which is part of the standard library. So we have our computationally intense function right here, and then a simple list for it to operate on and numbers. We're going to divide them into two different chunks that we're going to split into two separate processes. But how do we do this? Well, the simplest way for us to do this is actually pretty similar to what we would do with threads. We'll create two processes, and the way we're going to do this is by calling multiprocessing.process, and we're going to pass in a target, and that target is going to be our function up above, square sum, and we're going to pass in a tuple of arguments to square sum, that being chunk 1 for our first process, and then for our second process, we'll just change that to 2. So process 2 corresponds to chunk 2. So now we've defined two processes, but nothing has really happened yet. Thinking back to threading, you may know where this is going, and that is we need to start each of these processes. So we'll call process 1.start and then process 2.start. What this is doing when we call start is it's actually creating processes in the form of separate instances of the Python interpreter. And each of those instances has its own memory space and executes code independently of one another. So process 1 and process 2 will each do their own thing, not only separate from themselves, but from the main process that we're in here. And now that we got them going, we need to wait for them to finish. And the way that we do that is by calling process1.join, and the same thing for process 2. You can think of this like driving down a road. You start off on a single lane road, which is our main process here. When we create these two additional processes and we start them, we effectively created two more lanes on our road. In those two lanes, cars can pass us, we can pass other cars, we can do whatever. Each lane acts effectively independently of one another. That is, until we call join on those lanes. That merges those lanes back together, bringing it down into this single lane. With that said, let's save this and run it and see what happens. Okay, pretty quick. We see that sum of squares from numbers 10 through 50 was 5,500. And the sum of squares from the second chunk is 33,000. And just like that, with one of the simplest examples possible, we just did multiprocessing in Python. And it was really easy. And while you can introduce multiprocessing to your code like this, you're going to likely want to do this in better ways. And that's what we're going to cover with the rest of this video. So the first thing that I want to introduce to you is a better way of spawning processes. Now we can manually create them like we did with the previous example, or we can work with multiprocessing pools. For this example, we've got a helper function to check to see if a number is prime, as well as our workhorse function whose goal is to find prime numbers from some given number range. Those ranges specifically are going to be between 100 million and 101 million. We're going to use this variable here to control both the number of chunks as well as the number of processes that we're going to use within our pool. Okay, I keep talking about a pool, but how do we create one and what is it? First, to create a pool, we'll create a variable aptly named pool, which is going to call multiprocessing.pool, and it's going to ask for the number of processes that you want it to use. And for that, we're going to pass in this variable that we assigned before, which currently is 1. What this pool does is it gives us a number of processes to work with. It will evenly distribute tasks across the members in that pool. Because I do want to demonstrate the speed between the different versions of this, we're just going to do one member of the pool. meaning that everything's going to run sequentially, close to how it normally would if we didn't use multiprocessing at all. So let's store our start time. Now, one of the things I really like about this pool is that it's super easy to both create the processes and get the results with some of the helper functions that it provides. For example, we can go straight to getting the results of all of our calculations by calling pool.map. Just like you would use the built-in map function normally, see my video about that, you can do the same thing to map our find primes function to the chunks iterable. So for each of the chunks that we've created, it's going to run find primes. Now, of course, in our first example, this is just one process, one chunk. So it's just going to run once, pass the entire thing into find primes. But when we increase those processes, we're going to have more smaller chunks available to pass into find primes. Now we will need to collect all the results from all the find primes that are called. So I'll just do that now. So this is going to iterate through all the different results within that results iterable and add them all together, so we can get a true count of how many prime numbers we found between those ranges. Finally, we will close the pool and we'll also join on it. And at the very end of this, we're going to figure out how long it took by storing our end time. And of course, we want to print the results. Now, as I was typing out that print statement, I'm realizing that many of you may not be familiar with some of the syntax you're seeing here. Not only in the print statement itself, but also up here. How I'm able to put underscores within a number. Well, this is something that Python added a number of versions ago in Python 3. And that effectively allows you to, instead of using commas or decimal points, depending on the country that you're in and the standard that you use, you can use underscores to make large numbers more easily readable. This way, instead of having to have a bunch of zeros that they're hard to look at and immediately understand what number that is, you put in underscores and the interpreter effectively just removes them at runtime and uses the value as normal. And you can do the same thing when you're formatting the output in things like F strings. You put a colon and then the format. In this case, when we put a single underscore here, or we could also do a comma if you wanted to. But when we put an underscore here, it'll do the same formatting as we're doing above. This will make it more readable. Additionally, you can do the same thing with decimal precision. So if we do the colon here, and then we do a 0.2, meaning we're going to do a 2 decimal point precision, and then F, saying that's a float. We'll show what that looks like when we go ahead and run this again. So we'll save it and run it. And since this is just running in one process, it's probably going to take somewhere between 15 to 20 seconds or so. And with a shortcut, those 16.8 seconds have passed in no time at all. So we found 54,208 prime numbers between 100 million and 101 million in 16.68 seconds. Let's put an extra space there just for better formatting. Okay, so it took 16.68 seconds to go through all of that. Now, since we are using this pool, we can just bump that number up by 2. Everything else adjusts. Our multiprocessing tool now gives us 2 processes to run on, and we split this into 2 chunks. So we'll run this now, and we should see it complete in roughly half the time. Like I said, roughly half the time. There is a bit of overhead when creating each process. That's something to keep in mind with multiprocessing. Unless it's really worth going and creating additional processes, you probably want to keep it in a single process, because creating that additional interpreter does take a bit of overhead because it has to recreate a number of objects. Let's continue on, but we don't have to stop at 2. Let's double that again to 4 and run it again. This time it should take approximately 1/4 of the time as the original. Yep, and here we go, completed in 4.68 seconds. Now we are going to start to see some diminishing returns. If we double it again to 8 and run it, it completed in 4.21 seconds. You're not going to get a huge benefit for everything if you just keep throwing additional processes at it. There's certainly a sweet spot to this. And looks like for us, that sweet spot for time is probably somewhere around 4, maybe 5 processes. Of course, there's going to be a little bit of a margin of error here, depending on what else my CPU is doing. But yeah, with 5 processes, that's 3 less than 8. I got it down to within 0.03 seconds of using 8 processes. So in this case, I'd like to stop there and keep it at 5. Or if you want to be a little bit more conservative, you can put it back to 4, and it completes in 4.68 seconds. Something you'll want to think about when you're moving into multiprocessing. However, this isn't the way that I really like to do multiprocessing within Python. And in this example, we're not really passing data between processes after they're initially created. We effectively give them their chunks when they start up, and they go from there. So let's go into our final example of this video. And in this example, we do have a few more imports than we did before. The first one you may remember from our video on threading is concurrent.futures. Of course, we're going to be using multiprocessing, but probably not in the way that you're thinking of right now. And then a couple of things to help us down the line. For our quote, computationally intensive task, this one is going to be a lot more simple than the previous ones. We're not going to calculate primes or do anything like that. We're just going to count up from 0 to some ending number. So what are we going to use from the multiprocessing module if we're going to be also using concurrent.futures? Well, the multiprocessing module gives us a really nice data structure that can allow us to pass data back and forth between processes. And we'll do this also with a context manager. So create a new manager instance. And this manager gives us a number of tools that we can work with, but the one that we're interested in right now is a queue. Specifically, an instance of the manager's queue object. I like this queue object over other ones that are in the standard library because it has built-in synchronization. So you don't have to worry about any kind of locking to avoid conflicts between processes. This handles it all for you. Now, what are we going to do with this queue? What we're going to do is we're going to use it to populate the count to numbers for each of our compute tasks. You see here on line 10, we have count to is equal to queue.get. So it's going to try to pull a number from the queue. So let's create those numbers now. For blank in range 10, we'll say queue.put. We'll be adding a number to the queue, and that number is going to be random integer between, say, sure, we'll go 10 million and all the way up to 50 million. So we're going to be doing a lot of counting. And that's it. At this point, our queue is populated and ready for us to pass it to some processes. And to create our processes, instead of creating them manually or using the multiprocessing pool, we're going to use concurrent.futures process pool executor. And this is very similar to the thread pool executor that we used in the threading video. Here we can specify our max workers. This time we'll start with 4. If we don't specify max workers, which we can play around with later on, it will assign a number likely based on the number of CPUs that I have available on this system. But as you saw in our previous example, using the max number of CPUs isn't always worth it, but that's something we can play around with. So let's create all of our futures. Remember that a future is effectively a promise to execute some task. And the way that we create those futures is we submit our function compute task. We're going to pass in its task ID, which we'll call TID. Doesn't exist yet. We're going to also pass in our queue. We're going to do this for each task ID in range 10, corresponding to the number that we created here. At this point, just for readability, we may want to tell ourselves that we've submitted all tasks to the process pool. But what do we do with these futures? Well, of course, we're going to try to pull the results from them. Otherwise, they're not going to do us much good. So we'll iterate for I and future in. We're going to use enumerate here just to give us our I. And we're going to use another thing from concurrent.futures. And that's going to be the as completed function. And for that, we're going to pass in our list of futures. So what this will do is it will cycle through our futures, see which ones are ready. And as soon as one is ready, it's going to give it to us in this for loop. And at that point, we can pull out our results. So we'll call print first, just so we can talk to ourselves. Say that we're processing task. And since we start from a 0 index, we'll call I plus 1. And I guess since we're going to do non-zero starts here, we'll also go ahead and do that for our range here. So we have the same thing for IDs. And we're going to do that ID out of 10. And we'll put some dots there. Next, we'll get the result from that future by calling, you may have guessed it, future.result. And we'll print that out as well. Got result from task. This being, again, I plus 1. And we'll put in result. And we'll also format this because it's likely going to be a large number with an underscore. Now, before I forget, we also want to keep track of how much time all this takes. So we'll store start time. Let's go to time.monotonic. And at the very end, we're going to print out that we finished in the current time, which is time.monotonic minus start time. We'll wrap this all up here just for readability. We'll also do .2f, or 2 decimal places, and seconds. Okay, that's a lot of typing, and potentially some issues I'm not seeing there, but we're not going to know until we try to run it. Oh, looks like it's running. And completed in 4.46 seconds. So let's look through this. Okay, submitted all tasks to the process pool. Let's kind of even up the spacing here. And we see submitted all tasks to the process pool. Okay, so at this point, it's created all the futures by calling executor.submit. And then we see that we're starting task 1. And this message comes when we're in compute task, counting up to 16,887,628. So that's going to take a bit. We're also starting task 2, 4, and interestingly enough, 3 took a little bit longer to start up than 4. And we have a good range of values that each of these is trying to count up to. 2 and 3 are more than double of what 1 and 4 are counting up to. And it shows because task 4, which is only counting up to 12.6 million, finished first. Now, oh, I see the typo there, processing. Let's go ahead and fix that real quick. Processing. Steven, if you're watching, I'm sorry for the typo. Processing task 1 out of 10. But we said that task 4 finished. That's something you need to keep in mind with concurrent.futures when using as completed here, is that they're not going to come in the order that they were submitted as futures, but again, as the order that they completed. So if the order that they come in and the order that you store these results matter, you're going to want to figure out a way to put them in the right order. Now, one thing you could have done here is return the task ID as well as result in a tuple, so that way we can keep our order by the task ID. But we don't want to do this in our case. And then we get the result here. And since we know that processing task 1, 2, etc. doesn't really matter, as well as getting the result from that particular task doesn't really matter to the actual task itself, let's just look at which task finished at what time. So it then starts task 5, which only has to count to 10 million, and that finished before any of the previous tasks. Even task 1, which is only counting up to 16 million. So you see just how fast this is going. It then starts task 6, which is counting up to 30 million. And then task 1 finishes, and so on and so forth. Let's see which task finished last. And that coincidentally is task 10, which task 10 not only had to start last, but also had to count up to 35.5 million. Okay, so again, all that took 4.46 seconds. If we get rid of our max workers and let it use as many cores as it wants from our system, let's run that. See, all of them start at basically the same time, and it completes in 3.46 seconds. So it uses more than double the CPUs and gives us basically an additional second quicker runtime. And before we close this out, there's something really important that you need to consider when it comes to multiprocessing. And that is, in order to use multiprocessing, especially when it comes to passing data back and forth between processes, is that everything needs to be pickleable. If you're unfamiliar with Pickle, it's Python's built-in tool for object serialization, basically a way that it can export some type of object outside of a process itself, whether that's saving it to a file or passing it between processes. But Pickle is what Python uses for multiprocessing. But not everything is pickleable. For example, things such as lambda functions, nested functions, and classes not defined at the top level of a module, meaning nested classes, aren't pickleable. And you need to figure out ways to get around that, which isn't always easy. It's something I've had to deal with in the past. And in my particular case, aside from doing a whole bunch of workarounds, I ultimately decided to move over to using the thread pool executor, which doesn't require pickling because it all happens within the same Python process. But let me know if you want me to dig more into this in a future video. There's a lot more to multiprocessing, including pipes, but that's something we'll cover another time. And that wraps up this video. Now that you have a good understanding of how multiprocessing works and when to use it, give it a try in a project of your own and let me know how it goes. If you have any further questions or recommendations for others, leave a comment down below to let me know. As always, today's code will be added to the Understanding GitHub repo, so check the description for a link. And of course, if you have any questions or suggestions for topics you'd like me to cover, let me know in the comments section. To keep up with this series, please consider subscribing. Thanks for watching.